Hello, Dr. Chan. Can you hear me?
Yep, I can hear you.
Nice. Dr. Chan, if
Mhm.
you're not in the middle of a discussion, can I ask a question?
Sure.
Um, may you scroll down on your screen for assignment 8?
Okay.
I'll tell you when to stop. Keep on going. I just want to see the units. Show me the chart.
Hang on. Sorry.
So you're giving us, okay, go up. You're giving us English units here, pound force. Do you
Yeah.
want our submission to be in English units or in SI units?
Just be consistent. I mean,
Okay.
it's I gave it to you here in pound force just because I think that's just the default for this geometry. But
Sounds good.
just be consistent throughout your report. It doesn't
Thank you,
matter.
sir. Sounds good. Dr. Chan, I also want to say thank you for making the assignment due Friday instead of Wednesday.
Oh, sure. Yeah.
It's more doable.
Oh, yeah. Yeah. I know it's a busy time, so I think having more flexibility is always a good thing. All right, it's 7 o'clock. Let's go and get started. All right, good evening, everyone. How's everyone doing today? Doing good. Good. All right, so it's our last ANSYS activity. So this is activity 8. So this is our last one we're going to do together. It's the last time that we're going to be. You'll hear me kind of talking up here for the full time too. And so just like I talked about on Monday, the plan for next week is the plan for next week is that there's no plan. So and so I know final project is looming up very soon. And so I wanted to dedicate the 2 class lectures for next week to be kind of like project workshop or kind of like extended office hours, if you want to think of it like that. And so if you have questions on the final project, if you are if you're having trouble with the simulation, or you have questions on how to apply one of these activities to the final project, that's basically the perfect time to ask. And so I'm doing something similar for my other class too, 417. And so what I've been telling my students is that I know throughout the semester it's hard to kind of start on these projects kind of kind of a month ago, kind of when we posted this. But I would really encourage you to at least kind of get started on it before the class sessions next week, just so that you can come with questions. Okay. And so after next week, I'll still have my office hours. So even during finals week, I'll still have my office hours. They'll probably be virtual, just because I kind of live far from campus. But I do want to still make myself available. But the best time to kind of get a hold of me, where you'll have kind of my undivided attention and I'll be there for sure, is in the lectures next week and in the regularly scheduled office hours. And so definitely take advantage of that. And so if you come to class with questions next week, I'll do my best to kind of help you out. Okay. All right, so that's the plan for next week. So let's get back to the activity for today. And so the activity for today is buckling analysis, right? So it's kind of the implementation of what we talked about on Monday. And so what we have here is this kind of truss structure here. And so it's basically a bunch of truss bars kind of all kind of stitched together. And we're going to apply some loads on this. And we're going to do a couple of things. And so first thing we're going to do is we're going to observe kind of the stress stiffening phenomenon. And so I know we talked about it on Monday in terms of that simple beam, but you'll actually see it in action today too. So that's actually pretty cool. And then after that, we'll learn how to implement the eigenvalue buckling module in ANSYS, which is actually very, very simple. Okay. Okay, and so just like the normal kind of procedure for activity. So go to the Canvas site, go ahead and download the project instructions, download the CAD file, open up Workbench, and then we can get started from there. All right, are there any questions I can answer about this activity or the plan for next week, or just anything in general before we start? Okay, all right, so let's go and get started. So let me go ahead and open up Workbench. Okay. And just like last week, our first step here is going to be a static structural analysis. Okay. And so just like modal analysis, the eigenvalue buckling actually builds directly off static structural. Okay, so let's go ahead and take static structural and drag it to the workspace here. Okay, we're going to import our geometry. So we're going to right click on geometry, go ahead and click browse, and we're going to download and we're going to import the 3D truss geometry that I uploaded onto Canvas. Okay. All right, I don't believe we're doing any change in material. Right, so we're not doing any change in material, so we're just going to stick with structural steel. So let's go ahead and double click on model right here and open up ANSYS mechanical. Okay. And so when you open up ANSYS mechanical, you should be able to see the geometry. So it may be a little bit hard to see, but the reason the geometry looks a little bit weird is because it's already been converted to beams. And so what we have here is a collection of 1D beam elements, mostly just to keep the costs down. And so and this is kind of the perfect geometry for beams too. And so if we show, so actually let me see if I can display it here. Oh, it doesn't even show. But if we were to show this, you would actually see a bunch of kind of slender elements all kind of linked together like this. So this is kind of the quintessential kind of beam kind of example here. Okay. All right. So first thing we're going to do is we're going to mesh. So we're not gonna pay too much attention to the mesh here. And so the only thing we're going to make sure of here is that we're going to make sure we have quadratic elements. Okay. And for the element size, let's see here. Let me change the units here. So let me go to English units. Okay. Let me go to inches actually. And so let me make the element size here. Let's try an element size of 1 inch, and let's see how many elements that produces. We don't have to be too picky with the mesh here. We just have to get something decent. Okay. And so if you use an element size of 1 inch, you end up with about 3,000 elements. And so I think in the project specifications, it says 7,500 elements is good. So let's go ahead and cut this down to 1/2 inch and let's see what that looks like. Okay, so with 1/2 inch, we have a number of elements of 6,000. So let's cut this down a bit more. Let's try 0.3 inches. Okay. And so for 0.3, a mesh size of 0.3 inches, we end up with 11,000 elements. And so that's plenty. And so, you don't have to be too picky with the mesh here. As long as you're somewhere, above 5,000 elements, I think you're going to be good. Okay. But if you want to kind of follow along with me, I used a mesh size of 0.3 inches. Okay. All right. Everyone is able to load this geometry and get a mesh on this. All right, so far, pretty straightforward. So, hopefully that is good. Okay, so the next thing we're going to do is we're going to apply our loads and constraints. And so kind of the if kind of the geometry is a little bit unclear, basically what's happening is that this geometry is kind of sitting like this, and the ground is kind of down here. Okay. And so the first thing we're going to do is we're going to apply fixed supports. Okay. So we're going to apply fixed support on all 4 legs here. And so on the very bottom. Okay. So let's go ahead and insert our fixed support. And then I'm going to switch to vertex mode just to make it a little bit easier to click. And I'm going to click the bottoms of the 4 legs just like that. Okay. Okay. So now the geometry is fixed. So now we're going to apply the loads. And so there are 3 loads that we're going to apply here. So let me see. Okay. I think this is okay here. Okay. So let me go ahead and draw out the 3 loads that we're going to apply. So the first load is actually a combined load, but I kind of lump them together because they both kind of do the same thing. And so the first load that we're going to apply is a downward force on the very top of the structure. So this is load 1. And so if you're following along with the instructions, this is the axial load right here. I'm not going to do that. I'm not going to write in serial killer handwriting and so. Okay, so we'll call these load 1. Okay. So those 2 go together. Okay. The next load that we're going to apply is on this element right here. Okay, so we're going to have another load that kind of goes horizontal just like that. Okay. So this is going to be transverse load 1. So this is going to be load number 2, I guess. Okay. Right. And then we're also going to have a load on this element right here, or this beam right here. Okay. It's a little bit hard to see, but I think the figure in the instructions makes it a little bit more clear. So that's going to be load number 3. Okay. Okay. All right, so those are the 3 loads. And so the main thing to note here is that load 1, the 2 loads on top, this is going to put our structure in compression. Okay. And so that's going to be our main kind of driving force for the buckling. Okay? And so it's going to be our main driving force for the shear, the stress stiffening. Okay. And then for loads 2 and 3, these are kind of more smaller loads that we're applying just on the sides to basically induce buckling. So load 1, that's actually going to be the one that causes the structure of the beam to cause the bending stiffness to go down, just like we talked about on Monday. And the only reason we add loads 2 and 3 is just to kind of make sure that we do actually observe buckling, because you do need to have kind of some kind of bending force or some kind of transverse force in order to observe that. Okay. Okay. So let's go ahead and apply this. And so I'm going to go ahead and let's right click here and insert a force. Okay. Let's add the axial forces first. So I'm going to click on the top 2 points on the structure. Let's go ahead and apply. Okay. I'm going to change this to components. Okay, just so we can apply force in the Z direction. And if you go off the instructions on the PDF, the magnitude and direction of that force is going to be minus 5,000 pounds. Okay. Okay. So this force right here, let's go ahead and rename it. So this is going to be our axial force. In other words, it's our compressive force. Okay, either one is fine. Okay. Next, let's add in our 2 transverse forces. Okay. So we're going to add a transverse force. We're going to go ahead and apply it to the entire beam right here, because it's hard to kind of select just kind of one point on that beam, because it's kind of the whole beam is kind of one piece here. So I'm going to select this beam right here. And let's go ahead and change it to components. All right. And so this will be transverse load 1. And so this is going to have a magnitude of 100 pounds. All right. So let's go ahead and rename this. This will be transverse load 1. All right. And then let's go ahead and apply transverse load 2. So let's go ahead and apply another force. And so this is going to be applied on this member right here. Okay. Great. Let's do components, and this one will be in the minus X direction, so minus 100. Okay. So this will be transverse load 2. Okay. So in total, you should have 4 boundary conditions. So you should have the fixed support on the bottoms of the 4 legs. You should have the axial forces up top. That's our compressive force, and then our two transverse loads, one on kind of the upper part of the structure, and then one on the bottom part of the structure. Okay. All right. Any questions on this? Okay. All right. So for our results, let's go ahead and let's look at the total deformation. Okay. And then we're also going to turn on the beam tool. Okay. And so the beam tool is something special for a structure made of beams like this. What the beam tool will tell us is basically any kind of compressive or tensile stresses on the beam. So it basically shows the same thing as the equivalent stress, but it shows it as either a tensile or compressive stress on the beam, which is useful in this case. Okay. Okay. And so to do that, we're going to right click on solution A6. We're going to go to insert, and then we're going to go down to beam tool, and then you're going to select beam tool. Right. So I have no idea why it's a menu when it's just one thing. Okay. And so let's go ahead and select that. Okay. Yeah.
ANSYS will read which component of the beam.
Exactly. Yes. Yeah. And so because we've already kind of converted these elements or these structures to beams, it already recognizes those as beams. Yeah. But for a structure where part of it is beam, part of it's not, this will only apply to those beam. Yeah. Mm-hmm. Okay. All right. And so let's go ahead and run this. Okay, so we'll get our kind of our first preliminary solution simulation results. Okay, so you have the total deformation here, and if you're having trouble seeing this, because right now it's a little bit hard to see because of all the elements here. So that's what kind of all these black outlines are. So we can get rid of those. And so if you want to get rid of those, you can go to results here and go to edges, and you can click on no wireframe. Okay. So that's how you would basically turn off the edges of the elements just to make it a little bit easier to see, right? And so for the total deformation, you should get a plot like this, okay? And then under the beam tool, you can see here that we have a few results here, okay? Okay. Oh, let's do one more thing, actually, sorry. Okay. And so for one more result that we can show, just to make sure that we are seeing the axial results or axial forces, we can right click on solution A6, go to insert, go down to beam results, and then click on axial force. Okay. Okay, so let's go ahead and solve it one more time, just so we can see the axial forces. Okay. And so for the axial forces, you can see which sections here are in compression and which ones are in tension. Okay. Okay, so so you can see for the axial force here, the way that you kind of read these results, you can see here that we have both positive and negative results here. And so for the results that are positive in red, those are the beams that are in tension. Okay, so typically for a tensile force or a tensile stress, we typically show it as a positive number. And then for the results that are negative here, for the ones that are dark blue, those are the elements that are in tension or compression. Sorry. And so you can see here for all the dark blue beams here, those are in compression with a load of about 1,000 pounds. Okay. Okay.
Yellows are neutral.
Yeah, yellows are kind of almost neutral. Yeah. So between yellow and green, those are almost no stress. Yeah. Okay. All right. So the main results that you should see here are the total deformation. Total deformation is of course important. The axial force is something that is useful. Okay. And then you can also look at the direct stress. Okay. And so axial force and direct stress are basically the same thing. And so if you can see me switching between these, and the colors aren't changing at all. Okay. It's just the units that it presents it to you with are different. Okay? So for the direct stress, it kind of shows you the same information. And so it'll show you which beams are in tension and compression. But the units that it gives you, are in PSI versus the axial force. So it shows you the actual force. And so that'll be in pound force. Okay. And so for problem 1 of the report or problem 1 of the activity, I want you to show me the total deformation. I want you to show me the axial force and the direct stress from the beam tool. Okay. All right. Any questions on this? Everyone able to get these results here? Okay. All right, and so that's the static structural. So there's there's not really much to that, and so we kind of blaze through that. The next part of this activity is we're going to observe the stress stiffening effect. So we're not going to do eigenvalue buckling just yet, but I do want to show you that the stress stiffening result is actually real. Okay, and so if you remember from Monday, we talked about the fact that this whole stress stiffening effect is basically that when you apply a compressive stress to a beam or to any structure, what you're basically doing, or one kind of side effect of that, is you kind of lower the bending strength of that material. Okay, and so the more and more compressive stress that you apply, the weaker and weaker the element becomes in bending. Okay, and the opposite is true as well. And so if you apply a tensile stress, then it actually gets stronger in bending. Right. So the first thing I want you guys to do for this activity is I want you to basically observe this effect. Okay, and so we're basically going to do a buckling test manually. That's essentially what we're going to do. Okay, so the first thing we're going to do is we need to enable the stress stiffening, and so you're basically going to go to analysis settings up here. Okay, and so under static structural A5, you can see here that there is basically a section here for analysis settings. Okay, and we need to turn on large deflections. Okay, and so when you go to analysis settings here and you go to nonlinear controls. Okay, actually, where is it? Let's see. Oh, right here. Okay, and so under analysis settings, if you go to solver controls, you can see here there's one setting called large deflections. Okay. And so by default, it's off, right? Because it's if you turn on large deflections, it increases the cost of the simulation. But without the large deflections on, we wouldn't be able to see kind of the stress stiffening effect. Okay. Okay, so let's go ahead and turn it on. And let's go ahead and rerun the simulation and see what effect that has on our results. Okay, so with the large deflection turned on, it's a little bit subtle, but what you should see is that the deformation that you observe, it increased by almost about 10%. And so it used to be about 0.30 before, now it's about 0.32, okay? And essentially what's happening is that we're basically enabling all the nonlinear effects, in this simulation, okay? Which normally, normally when you enable nonlinear effects, it's going to increase the cost of the simulation pretty significantly. But because we have a structure here of all beams, it's pretty cheap, okay? Okay, okay. And so you can see here that under the current configuration, we have a total deformation, a max total deformation of about 0.327, okay? And that's occurring here on this beam here. One of the beams that we applied are transverse stress, right? Let me show you something. So, go ahead and memorize that number in your head. So go ahead and memorize that 0.327. And what I'm going to do here is I'm going to increase the value of this axial force, okay? Because right now we're applying a compressive force of about 5,000 pounds. Let me double this so you can kind of see what's going to happen. Okay. Okay. And so I've doubled our compressive stress here. And so by our logic, since we're applying more compressive stress onto the structure, the structure it should buckle more. Right? And so the deformation that we observe should be higher than it was before. And in fact, it is, right? So you can see here that when we basically double the amount of compressive force, the maximum deformation here increases to almost about 0.37. So, it's a fairly significant difference. Okay. All right. And so for this part of the activity, problem 2, so I'll go ahead and give you guys, it'll probably take you guys maybe 10, 15 minutes to gather all this data. I want you to basically create a line plot. Okay. And so I want you guys to create a line plot in Excel, where on the x-axis here, we have the axial force. And on the vertical axis, I want you to plot the deformation. And so for various values of the of the compressive force. And so I want you to basically change that axial load. And so I want you to go from basically minus 10,000 pounds to 10,000 pounds. And I want you to plot out what the maximum deformation is going to be. Okay. And what you should see, I can bring back the pen here. What you should see is that the trend line should kind of go down. Okay. And so at minus 10,000, you should see a maximum of the compressive of the deformation. Okay. But then as you change that load to tensile, then the deformation will go down because of that stress stiffening effect. Okay. And so you're going to have to use Excel. And so you're going to have to use Excel to kind of plot this out, but I want you to kind of change that axial force and plot it out just so that you can see. Okay. So you should have about 20 data points overall, because I want you to change it in increments of 1,000 pound force. Okay. Okay. Any questions on that? Does that kind of make sense for everybody? Okay, so I'll give you guys maybe like 10, 15, 20 minutes to kind of get all that data and plot it out. You can use Excel, you can use Google Sheets, you know, it doesn't matter to me. You can even draw it by hand if you're confident in that. But why don't you guys go ahead and do that just so you can kind of see the stress stiffening effect in action. Okay. Oh, question, yeah.
Look at this.
So both of these forces we are doing perpendicular to, and so you know I think probably in the thing, you know, this may be pointed inward, this may be pointed inward like that. It doesn't really matter because these are perpendicular to the actual beam. Yeah, so it's compressive. It would be compressive for the entire structure. Yeah, and so if you kind of switch beam direction, yeah, it would point towards the structure. But for this beam by itself, it's kind of perpendicular.
This, and I put the transfer one of these and the second one here.
Yeah.
So when I did that way, it became compressed.
Yeah.
So that's when we like to do it. So it doesn't matter.
It shouldn't matter for me. The main ones that are going to be bending are just whichever one. You should see the same effect.
Yeah.
And then also for this question here, you can see I have kind of additional questions that you can answer, but you can save those for when you write up the report, so you don't have to answer them just yet.
Professor.
Wait a second. Oh, analysis settings. It is under solution or under static structural A5. This one right here. Yeah, and then you want large deflections right here. Sorry, Chris, you were saying something?
Yeah, I showed up a little late. Is it for the axial force and transverse force or transverse load? Is it just force?
Yes.
Okay.
Yeah, it's just those are just forces.
Are we for the transverse? Are we applying it to the beam or a point?
The beam. Yeah, the entire beam.
Okay.
Mhm.
Anywhere specifically on the beam? Since it's
just select the whole beam. I think you can only select the entire beam, so just like that. Yeah.
Okay.
Transverse load 2 location. Yeah, it's for transverse load 2, it's on one of the legs basically. So just somewhere one of these legs on the bottom. Because there's so much symmetry in this structure, so it doesn't matter too much which one you apply it on, but just one of those bottom legs. Yeah. Mhm.
And where are we applying the fixed support? The base, those 4
Yeah.
points?
So basically all the bottoms of the legs. So all 4 of these points here. Yeah, those, oops, not that one.
And any specific requirements for meshing?
The mesh, you don't have to be too careful with this one. As long as the
Do
number
you
of
want a
elements
method and a
over.
sizing?
Wait, say again?
Do you want a method and a size?
No. For
Because
here,
it
you can
says
just,
7,500, what was it? 7,500 elements.
yeah. So you
Um,
can just change it by the global settings here. So as long as the element order is quadratic here under mesh, and then I use an element size of 0.3 inches, but anything like 1 inch or 0.5 inches is fine. Yeah, we don't need that too big of mesh here.
Okay.
All right, so how's everyone doing getting that plot? It's a lot of data points, so.
Materials, structural steel?
Yes.
Anything specific about the geometry we need to worry about?
No, everything is made of beams already. And so, it's already kind of prepped for you. Yeah, so there's nothing too special with the material or geometry here.
Okay. Is there any way to get the display to put it right side up instead of all cattywampus?
You can I think the best way would be one of these kind of use kind of the coordinate axis here in the bottom right to kind of click to kind of set it to one thing, and then just kind of rotate with your mouse to kind of get it to a good position.
Okay.
Oh, Chris, there is one thing you have to do. So before you run the simulation, you're going to go to analysis settings here under static structural A5. And then there's a setting down here for large deflection. And so you're going to want to turn that one on.
Yeah, I heard that and forgot to do it.
Okay. Yeah, just make sure you do that before you start doing problem 2.
What happens if I do that before I start? If I fail to do that before I start, does it explode?
Oh, no, it's fine. It just modifies the results a little bit. So if you turn that off, basically it's going to assume that everything is linear, and so it'll basically essentially what it'll do is it'll underestimate the deformations because buckling wouldn't be able to take place. And so in order for you to observe buckling, you have to turn that large deflection on.
Okay.
Since we can't do 0, do you want like some low number?
Oh, you can skip over 0. Yeah. It'd be a fairly linear graph. 0 is kind of right in between. This is the most time consuming part of the activity. So, that's why we're doing it together. After this, it gets a lot easier.
I have a question.
Sure.
We're dropping one of the activities, right?
Yes. Yeah. The
Okay.
lowest one,
So
the
if
lowest
we've
one is
done
dropped automatically.
7 already, we can drop this one.
Correct. Yeah.
Okay.
Yeah, this one is one of the more easier features though, and so a lot of people end up using this one for their final project. So this just kind of gives you practice for it. But in terms of just your grade, if you did all the other activities and you did well in them, then you don't have to do this one. It'll be dropped automatically. How's everyone doing on this this part here? Good. Okay, so I'm gonna go ahead and move on. I know probably some of you might still be gathering data for this problem, but you know, you kind of get the general idea, right? And so what you should be seeing in your plots is that as you make the load more and more compressive, then the deformation goes up, because remember, the bending stress goes down the more compression you put it in. That's the idea behind buckling. Okay. All right. So that was buckling the hard way. So you know, that was kind of you know, I kind of made that a little bit painful on purpose, just so that you can see, you know, normally it's very kind of painful to do this kind of buckling analysis, kind of, you know, just kind of naively. Okay. All right. So now I'm going to show you how to do buckling the easy way. And so, you know, we're basically going to use another analysis type, just like modal analysis. So we're going to need to close ANSYS mechanical. But before we do that, I want you guys to go to your axial force here. And I want you to make sure that the force that you're applying is compressive, okay? The actual value doesn't really matter too much. You just want to make sure that it's a negative number. So you can be like a negative 1,000, a negative 100, you know, just make sure that that's compressive, because that's the next step that we're going to do kind of depends on that being compressive, okay? And so, you know, make sure, you know, I'll kind of say it again, make sure your axial force here is compressive. Then once you do that, you can go ahead and close ANSYS mechanical to bring you back to workbench. Okay. Magnitude doesn't matter, as long as it's compressive. That's the okay. Okay. And so after you've changed, and if you want to get rid of these lightning bolts, you can rerun the simulation, but you know, it doesn't matter too much. Okay. Okay. And so the next thing we're going to do is we're going to take eigenvalue buckling. And so it's a different analysis type here from the toolbox. So we're going to click and drag eigenvalue buckling, and we're going to drag it on top of solution, just like this, okay? Because what we want to do is we want to basically link the eigenvalue buckling to our static structural analysis, so it'll inherit all the boundary conditions and such, okay? Okay, so after you click and drag eigenvalue buckling onto solution, it should look like this. And so you should see the two are linked. It should have the same engineering data, the same geometry, the same model, and the same solution, okay? And so once you do that, you can go ahead and double click on setup for eigenvalue buckling, and that'll open up ANSYS mechanical again. Okay. Okay. All right, so now we're back in mechanical, and so you can see here that we have our geometry here. Right? I have lightning bolts because I changed the component of the axial force, but you know, it'll come back away just as soon. Okay. All right, so this is buckling the easy way. And so you know, the nice thing about eigenvalue buckling is that it's really kind of a one button solution for buckling. Okay, so you know, let's try just solving it as it is. So without changing any settings, let's go ahead and hit solve, and let's see what it gives us. Okay. All right, and so if we click on, after it completes, you can click on solution B6, okay? And what you should see here, the main result is going to be in the bottom right-hand side, bottom right-hand corner of the screen, okay? And so you can see here, it's showing the result as a load multiplier, right? So remember, we talked about this on Monday. So remember, the way ANSYS is going to display these results is it's going to tell you how much you need to multiply all the loads in your simulation in order to achieve buckling. Okay. And so for my results here, you know, what this is telling me is that if I increase the magnitude of all my loadings by a factor of 14.135, that's going to be enough to cause buckling. Okay. So your multipliers are going to be different. And so, you know, if it really depends on what value you chose for your axial force. Okay. So for me, I chose a force of 1,000 pounds going downwards into the model. Okay. And so that gives me a load multiplier of about 14.135. Okay? And so if you look at the activity sheet, you can see here that the load multipliers there are a lot smaller. That's because I probably used a different load value there, and I don't remember what I put for that one. Okay, so you can see here that it's showing us two modes here. And so we can show more. And so I think in the activity, I asked you to show 6. So let's go ahead and do that. Okay. And so under the eigenvalue buckling, you can see here that there's another button here for analysis settings. Okay. And then here, one of the options here is the maximum modes defined. So let's go ahead and increase this to 6. Okay. And then let's go ahead and solve it again. All right, and so with 6 modes, you can see here that we have six load multipliers here. Okay. All right, and so the last thing I'll show you here is how to actually display these modes. And so remember, buckling, the way ANSYS displays buckling is very similar to modal analysis. And so when you do have buckling that's occurring, ANSYS, it can give you a prediction in terms of how exactly the buckling will occur or what it will look like. And so the way that you can display that is you can highlight all the load multipliers here. You can right click this, and then you can click on the button here for create mode shape results. Okay. Let's go ahead and click that. And so it's going to create 6 deformation fields for you. So let's go ahead and show what that looks like. Right. And you can click on each of the deformation modes and see, how the buckling is going to occur. Okay. Okay. And so you can see here, under my arrangement right here with the way I have the forces, your transverse forces might be a little bit different. So your mode shapes might look a little bit different. I think for the activity, or actually the activity, it's in that leg as well. But you can go to the different parts here and it'll show you which legs will basically buckle. Okay. And so basically what this is telling you is that if this structure were to buckle, this leg right here would be the first one to go. So that's the one that's going to collapse before all the others. All right, and so that's it. And so that's buckling right there. And so that's, you can see here that, I had you start with buckling the hard way, right? But this is kind of like, an easier way to do buckling. And so if you want to do just kind of a quick and dirty analysis in terms of, predicting whether buckling will occur, this is how you would do it. Okay. All right, any questions on this? Okay, all right, so that's the activity. And so, the rest of the activity here is I basically want you to kind of repeat it. And so, problem 4 is going to have you change the material. Problem 5 is going to have you change the load configuration. Okay. But it can be pretty tedious to kind of do both of these. And so what I'm going to do is I'm going to make a change here where, instead of doing both problem 4 or problem 5, you can choose either or. And so, you have to do problems 1 through 3. And so that's kind of what we did together just now. So problems 1 through 3 we did together. But for your activity report and for the rest of class today, you can choose to either do problem 4, where problem 4, you basically repeat problems 1 through 3, but you change the material. Okay, so you change it from structural steel to something else. Or you can do problem 5 where you change the loading. Okay, and so maybe you add an additional axial force, maybe you add some additional transverse forces. Basically you change the loading to something else.
And
okay.
Dr. Chan.
Yes.
So having said all that, for our homework submission for assignment 8, we could choose problem 4 or problem 5. We could avoid ignore one of those problems.
Exactly, right. So I want you to just choose one or the other. And I'll send an announcement to kind of make it official too. But
okay,
yeah, you can, but for the activity, just choose one or the other. So you don't have to do both. All right, and then after that, it's just the summary. And so, probably, you guys should be able to knock out all the simulations today with the time remaining. And so, choose either problem 4 or problem 5. I think the thing that's going to be time consuming is problem 2, which is getting all this kind of stress stiffening data. But once you have that, then it's pretty straightforward. Okay. All right, any questions on the rest of the activity?
I have one.
Sure.
Problem 2, keep the 2 transverse loads constant, vary the axial load from 10,000 to negative 10,000 in increments of 1,000, and observe how any suggestions how to do that I must have missed? the suggested how we do that.
Oh, yes. So for this part right here, what you're gonna do is for this axial load here, or this axial force, right? The Z component of this is I want you to basically vary it from 10,000 to minus 10,000. So you're gonna run a simulation with this equal to 10,000. So you're gonna solve it. And so you're going to see the total deformation. And so you're going to see the deformation here is 0.247. And so you're going to log that into a spreadsheet. Okay.
Okay,
And so you're going to say for an axial force of 10,000, I get this deformation. And then I want you to basically change this to from 10,000 to 9,000.
okay,
And then just basically do the same thing. And so you're going to have basically 20 points of data where you see is that deformation is going to change as you change the load.
is there a way to do that in ANSYS instead of doing it manually?
I think so, but I think just just for something like this, it's it's better just to do manually.
Okay,
Yeah, but there is a way to automate stuff in ANSYS. I'm just not aware.
okay,
Yeah, and basically what you're seeing here is that you can see that what we're the load that we're varying here is kind of a force that's kind of pushing up top. Right? But the deformation that you're seeing is actually a bending mode. And so the kind of the difference in the deformation that you're seeing is because of stress stiffening and buckling. And so even though this deformation goes kind of perpendicular to the part, the main kind of cause of it is the change in the compressive or tensile.
okay.
Mhm.
Thank you.
Dr. Chan, is that the end of today's lecture?
Yep, that's the end. And so you can stay for the next 30 minutes. You can work on either problem 4, problem 5, or if you want to watch NBA or something, you can go leave and do that. So yeah.
I just want to say thank you for being such a great instructor, Dr. Chan. I greatly appreciate it.
Of course, yeah. Thank you for being a great student. So I mean, I'll
Yes, sir.
see. I mean, hopefully I'll see you next week. So remember, next week is the project workshop. So
Agreed. Have a good night, sir.
thanks, you too.
Thank you, sir.
Have you figured out if you're gonna be teaching viscous fluids next semester, or did they not
I
tell
have
you?
not. No, I haven't.
Okay.
I haven't heard any news from that yet. So
Okay,
they'll probably tell me like during finals week. That's
I'm very interested in that class also.
yeah. It's either going to be me or it's going to be Dr. Myral that teaches it. So one of us is going to teach it. But I haven't taught a fluids class in years. Not even the undergraduate fluids. So I'm a little bit out of practice for fluids, honestly. I like the class though. I like teaching it, but we'll see. Let me make that announcement. Yeah.
So.
Yeah, so the model analysis is present.
So. What has to. But now since. I think it's only four, so I don't know. Analysis before that.
I see. So the model analysis will still tell you, if an earthquake would occur, the frequency.
But does that not estimate the height?
Yeah, they are two different. So if you actually want to see your building at apps, you would have to do frequency response.
Yeah, but what about this? So think of an example that I'm trying to do this building is direct. The direct has a room. So we have in one floor there are different. Like each floor has a different border. The block.
Yeah.
So what if I say that one block is one room? Say for example, one the wing shed, one floor. Downstairs one kickboxing and
Yeah.
and I had different forces. I had to pack load and then do a more analysis. So what would that make sense?
Yeah.
It's a triangle equal X. So there's no external force, it's just a load that goes inside the building.
Yeah.
So instead of doing all of that, we can make it simpler.
Yeah, no, that would work, just so you can see the effect on each. Yeah, no, that would work. So, for the project, we kind of did over the last, 5 weeks or so, we kind of did kind of a speed run of all these features, but of course, these features go a lot deeper than what we showed too. So, it is definitely still possible to apply that external force for like an analysis. The way you would do that is to look at frequency response. That's perfectly fine. You can have that. You don't have to restrict yourself to just kind of what we did frequently in class.
Yeah.
And so, you can feel free to add more. It's just a lot of that's going to be kind of on your own, just because just so we can have.
Like you told me to show like static. So when I do it now, so this when I show this will be the static first.
Yeah.
And then I show this, right?
Yeah.
So the first one is take the static analysis static.
Yeah.
But can I repeat the same this one or like a completely change one?
No, you can keep the same average. So if you look at the rubric, so you should look at the rubric. So what I'm going to be looking for is basically in your results section, there should be static result 1, and you're showing like deformation stress that we kind of talked about it. Static results 2, showing the deformation stress, static results 3. So I'm looking for those 3 sections and 3 plots of like deformation and stress with either 3 different boundary conditions or 2 boundary conditions. So that's basically the same as the first image. And then after that, I'm looking for additional sections. And this is my goal. You can use the same boundary conditions as this one, but then the modal analysis results
Like we have to show all the 60 information
exactly
with the frequency.
exactly. Yeah, so I want that to be separate from like the static. But you can use the same match the same boundary.
Okay, if it's not like this one, I will show like is it okay if I just show you an example of what I was talking about? So what like so I just like this the start is generate the start and then add one. Boundary condition be like it's obvious that these bottom points get fixed.
Yeah.
And then when I was talking about adding forces, so I'll just say like I added this.
Yeah.
And say that minus 3,000 on this floor.
Yeah.
And then the next force be for this flow.
Okay.
Professor,
I'll be there in a second.
So this will be like my first level.
Okay.
And then. For these courses, I just.
Oh, okay, I see what you mean. You can keep some courses.
Individual now change, and now I'm thinking of changing, so last time 3,000 then.
Yeah.
So now I'll just make it like.
Sure. Yeah, so remember, right now, you're not inheriting into the boundary status from it. It's basically, so the way you would inherit, you go to pre-stress right here. Who am I giving here?
Oh, okay, I should, I just.
This is just a.
So now I like, could I explain this in such a way that this room is one thing, this room is one particular thing, this is another thing, so that's why all. We divide in courses in each room.
Yeah.
It's gonna be different.
Okay.
So this, would that make sense?
Yeah.
Then I show all the six of these.
Yes. Yeah, so remember, any force you apply there, those are static forces. And so what those are gonna do, they're gonna add pre-stress into your structure.
Yeah.
And so those are gonna change the frequency. Just doesn't make that big
Yeah.
difference. So, for this case, you would say that this is what the modes would look like if we had possible weights in these particular groups.
Yeah. Yeah, because the next set has different things.
Exactly.
So that's what I was just talking about.
Yeah, no, that makes sense. Yeah. Right. Yeah. All right, sorry about that. I was helping someone in the class. Someone had a question?
yeah, sorry about that.
Uh-huh.
Hey, Professor, I took a nap for this class, but I overslept.
Okay.
Yeah,
no
I'm sorry. Yeah, it was one of those days today at work. I had a quick question for the additional method. You know how we have to do 3 scenarios?
Yes.
Can I pick my favorite one, or is there one we have to pick like absolutely to do the additional method on?
It can be any of them. It's it can also be something completely different too. But someone was just asking me that too. So basically for one of their additional features, they're going to do modal analysis. And so they're going to take their boundary conditions from scenario 2 and just keep those the same, but then show the result from the modal analysis. And that's totally. Yeah.
Okay, thank you. Yeah, that's what I did for one of my scenarios, like with like a crash. I want to see all the vibration and the frequency and how it would look like.
Yeah. No, that's
and then-
perfect.
Thank you. Yeah, and then one more thing. When will you be posting the video on this tutorial?
For activity 8,
Yeah,
probably tomorrow morning. That's when I usually do it. So I have a lecture 8:30 in the morning on Thursdays, and then I usually upload them all at once. Yeah, at that point.
Thank you. I appreciate that. Have a great rest of your night.
Thanks, you too.
Thank you.
I understand.
Professor,
Yep,
I just have a quick question in regards to activity 7.
sure.
So for problem 3, when it says change the material for one that is stiffer, i.e. higher Young's modulus, and one that is lower,
Yep.
when it says show all 6 deformation fields, are you referring to a specific one, whether it's pre-stressed or stress-free?
Either or, and so it can either be pre-stressed or stress-free. I think the stress-free will be a little bit easier to do.
Interesting. And then do you want us to show both materials, so i.e. 12?
Yes. Yeah, both
I
materials.
Okay. Perfect, thank you.
Yep.
I think I'm the only one here, so. But yeah, that answers my question, Professor. Well,
Okay.
thank you very much. Have a
Yep.
good night. I'll see you on Monday.
Yep. See you Monday.
Take care.
Everybody, any final questions before wrap it up? Yeah.